This is Luke Seibold from PhyziX, and today we're going to be looking at the basics of rocket science, projectile motion. Alright, now let's start applying what we've learned to the real world with projectile motion. So let's imagine we got a little dude over here, and he's throwing a ball through the air. Ball, when you throw it through the air, is going to move with a parabolic arc. Now, as the ball is moving through the air, it is actually going to have a constant horizontal velocity. So no matter where it, let's just change that to a different color. So no matter where the ball is across the plane, it will always have the same velocity. What I'm drawing here are velocity vectors, and these show the magnitude and direction of the ball's velocity, but they're only showing it in the horizontal direction. And so the direction is given by which way the arrows are pointing, and the magnitude of the velocity is given by the length of the arrows. Now, the ball is constantly changing direction as it gets closer to the top. Once it's at the very top, it's moving completely horizontally, and it gets more vertical as it gets towards the bottom. So what we're going to do is break it up into its vertical and horizontal components. So here we've shown the horizontal components of the ball as it moves through the air. Now we're going to look at its velocity. It's the vertical component of its velocity. So as it's initially thrown, its velocity is at its greatest, and then as it loses that initial velocity, because acceleration is acting down towards the earth, the velocity gets less and less until it's actually zero up here. The vertical velocity at the peak of the arc is at zero, and then as it starts to decline, the velocity increases downwards until it is at its maximum down here. And actually, no matter whatever height it is at, the velocity upwards will be the same as it is downwards. So this velocity is actually the same as this, or sorry, I should say the speed of this is the same as the speed of this, because the direction here is downwards, whereas up here it's upwards, so the velocity can't be the same. And this is all because of the acceleration due to gravity, which is constant and always acting towards the Earth. So these acceleration vectors are always the same length, always acting down towards the Earth. And as we learned previously, the acceleration due to gravity, or g, is 9.81 meters per second squared. So these are all given by g. So it has constant downwards or negative acceleration towards the Earth. So let's take a look at how we can represent this graphically. So first, let's take a look at the x direction. So all the motion in the x direction, or the horizontal direction. So first, let's take a look at how this can be represented with a displacement time graph. So on the y-axis, we're going to have displacement, and on the x-axis, we're going to have time. So as we know that it is moving with a constant velocity this way, we'll call this the positive direction. So in every increment of time, it is moving at a constant displacement. So this means that the displacement is proportional to time, and it's moving linearly with a constant velocity, as we learned previously. Now, if we're looking at a velocity time graph, we know that the velocity is constant. However fast this little dude threw the ball, that's how fast it's going to be the entire time. And so it will be just a constant flat velocity the entire time. And finally, let's just put a little time there. If we are looking at the acceleration time graph, then the acceleration is 0 because the velocity is not changing. So as there's no rate of change in velocity, then there will be no acceleration. So it just stays at 0 the entire time. All right, now let's take a look at the motion in the y direction. So first, let's take a look at a displacement time graph. Displacement on the y-axis, time on the x-axis. And so as we can see, the velocity starts off initially really high as he whips it out of his hand, and it gets slower and slower until it reaches the top where it has no acceleration whatsoever. So this means that the gradient must be getting less and less until it's eventually 0, where the vertical velocity is also 0. And then as the velocity starts increasing towards the Earth, the velocity starts increasing in the negative direction, so the slope becomes greater and greater in the negative direction as it comes back towards the origin in terms of its vertical displacement. So the next graph we're going to look at is the velocity time graph. All right, now let's take a look at the motion in the y direction. So first, let's take a look at a displacement time graph. Displacement on the y-axis, time on the x-axis. And so as we can see, the velocity starts off initially really high as he whips it out of his hand, and it gets slower and slower until it reaches the top. So this means that the gradient must be getting less and less until it's eventually 0, where the vertical velocity is also 0. And then as the velocity starts increasing towards the Earth, the velocity starts increasing in the negative direction, so the slope becomes greater and greater in the negative direction as it comes back towards the origin in terms of its vertical displacement. And so as you can see, it has the same parabolic arc in the vertical direction as it does in real life, where he throws it with this parabolic arc. So the next graph we're going to look at is the velocity time graph. And so as we can see, the velocity is decreasing at a constant rate until it's eventually 0. So we show that by the velocity decreasing at a constant rate until it reaches 0. And then it changes direction. So this means that the sign has changed, and now it's negative. So if this is 0, it's become negative, and it's becoming a greater and greater negative number as the velocity downwards increases. So at this point, it's at the top of the arc, and then it continues downward in the same linear pattern, increasing negatively. And so finally, we're going to take a look at the acceleration time graph. Acceleration time graph. And so we know that the acceleration is constantly downwards in the negative direction, and the value of acceleration is the acceleration due to gravity, which is 9.81 meters per second. So if it's constant and it's negative, it will constantly be at this value, which we know is 9.81. So there you have it. Now you have all the equations, graphs, vectors, and little stick people you need to know how anything gets from point A to point B.